Hi, I'm Deepak Dey. I'm a Board of Trustees Distinguished Professor of Statistics in the University of Connecticut, Stores, Connecticut, USA. In today's lecture, I will talk about how to find the posterior distribution of the normal mean mu given that sigma square is unknown. What we'll do in a step-by-step approach that we'll put a prior on the parameter mu as well as on the prior on the parameter sigma square, and we will show through the derivation that how the posterior distribution of mu can be obtained given the data, and how the posterior distribution of sigma square given the data can be obtained. And you will see that we choose the prior of mean mu is again normal, but sigma square is either inverse chi-square as a special case or inverse gamma distribution. But then you will see at some point under certain scenario the closed form expression may not be possible, and therefore we have to use sampling based approach, and one of them is called Gibbs sampling, which is a special case of a Markov chain Monte Carlo approach. Today's lecture will talk about Bayesian analysis of the normal distribution, part 2. Initially, we set up the basic model of a normally distributed random variable with unknown mean and variance, a two-parameter model. We will discuss philosophies of prior selection and implementation of different priors with a discussion of MCMC method. MCMC stands for Markov chain Monte Carlo. So these are the three learning objectives in today's lecture. Now we've clarified the MCMC. So we'll talk about simple example of MCMC. As I mentioned, MCMC stands for Markov chain Monte Carlo, and it's really a numerical integration approach. So let's talk about that in general. So as it may be becoming apparent, the greatest practical difficulties in Bayesian inference is computing the integrals. In fact, except for simple cases like conjugate priors, researchers lacked the ability to do Bayesian analysis. This integration must be done to identify the marginal posterior distribution, which is the object of analysis. Many Bayesians suggest that the inability to compute these integrals is the only reason why we use the hypothesis testing framework today. Markov chain Monte Carlo, or MCMC, is a computationally intensive simulation method to replace exact integrals developed in the 1980s, made it possible to tackle more complex realistic problems. Let's talk about basics of MCMC. The goal of MCMC is to use simulation so that we can take a large number of random draws from the posterior distribution. The resulting sample can be used to estimate the posterior mean, median, Bayesian credible interval, that is HDR, etc. In class, we will implement the Gibbs sampler, the most common form of MCMC. Here, we can talk about winbugs, the R code, many approaches are there. You will see in the notes, there are all the details. One of the approaches called bugs, which is known as Bayesian inference using Gibbs sampling. We'll generally duck the details of how the program is making its calculation, but it really is not that complex in theory. Let us talk about the intuition behind the Gibbs sampler. We consider a problem with two parameters, say θ1 and θ2, and let x denote the data. Suppose further that we know the conditional distributions of P of theta 1 given theta 2 and the data x, and P of theta 2 given theta 1 and x. We need to find the posterior distribution of theta 1 given x and theta 2 given x. So our goal is to find the posterior distribution of each parameter, theta 1 and theta 2, given the data. On the basis of the information we have, the conditional distribution of theta 1 given theta 2 x and theta 2 given theta 1 and x. So these are called complete conditionals through which we wanted to find the posterior distribution. The Gibbs sampler proceeds by choosing some initial point or starting value, which we will denote as theta 1 superscript 0, theta 2 0 from the parameter space. This can be reasonable value of theta. For example, sometimes we can take even the maximum likelihood estimate if possible. Then we take draws from the two conditional distribution in the following sequence. We choose theta 1 superscript 1 from theta 1 given theta 2 0 and y or x. Earlier I used the notation x for the data, now we switch to y. Then theta 2 given 1 from probability distribution of theta 2 given theta 1 superscript 1 and y, and theta 1 2 is from theta 1 given theta 2 1 and y, and theta 2 2 will be theta 2 given theta 1 2 y, and theta 1 3 will be theta 1 given theta 2 2 and y, and theta 2 3 at the third iteration stage is theta 2 given theta 1 3 y. Notice that the superscript indicates which stage you are in. So 0 for initial, and then 1 is for first stage, 2 is for second stage, and the superscript 3 indicates the third stage. So notice that here we have two parameters, theta 1 and theta 2. We are taking the sample in a repeated manner at different level. This sequence of draws is a Markov chain because the values at step t only depends on the value at step t minus 1. If allowed to run long enough, the Gibbs sampler will converge to the true posterior distribution. If allowed to run for sufficiently long after convergence, the Gibbs sampler produces a complete sample from the distribution of theta. This algorithm can be easily generalized to the n parameter case, theta 1, theta 2 up to theta n. For the tth iteration of the Gibbs sampler, we have theta 1 superscript t is sample from or a draw from theta 1 given theta 2 t minus 1, theta 3 t minus 1 up to theta k t minus 1 y. So what you can see that at tth stage, every draw of the parameter is taken from its complete conditional at the previous stage. And that process is continued until we cover theta n. So we'll talk about in further this modern parametric Bayesians and the normal model. So again, we have y is normal mu sigma square, sigma square mu both unknown, and what prior distribution would be a modern parametric Bayesian choose to satisfy the demands of convenience. What if we use the definition of conditional probability? So P of mu sigma square is the joint distribution is product of mu given sigma square times P of sigma square. So we know that we have already showed or already mentioned earlier that joint distribution of P of mu and sigma square, joint posterior, is normal inverted chi-square. 4 parameters in the prior, and mu give sigma square is normal inverted chi-square with parameter mu0 sigma square over k0 and v0 sigma 0 square. Because this is the conjugate distribution for the normal distribution with unknown mean and variance, the posterior distribution will also be normal inverted chi-square. The posterior, we all know, this is a repetition, I'm repeating the previous lecture. The posterior distribution of if y is normal and mu sigma square normal inverted chi-square, then joint posterior mu sigma square given the data is normal inverted chi-square with parameters mu n sigma n square over k sub n, Vn sigma n square, where mu n is the weighted average of the prior mean and the data, and all the expressions are given. Now we can also factor the posterior distribution just like the prior. So in summary, after the factorization, we can mention that mu given sigma square y is normal mu n sigma square over kn, which is a normal with mean expression is given there and variance. And further we can integrate out sigma square to find mu given y is student t distribution with parameters given in the slide. These are essentially the same posterior distributions as we found with the improper priors. To implement the conjugate priors in wind bugs, we would use the same code, but substitute the values mu n sigma n square over kn, Vn sigma n square into the posterior. So if we have y is normal mu tau, what priors we would choose for mu and tau? I would choose mu normal 0t, tau is gamma AB, where AB are small numbers, where t is a large number, that means it's a flat idea, the variance is large. This is because we expect something like the central limit theorem to hold, then the distribution of the sample mean should be approximately normal for large n. And gamma choice is done because the distribution is bounded below at 0, and unlike the chi-square distribution which shares the property, it is not constrained to have an equal mean and variance. Note, we know we have to talk about the mean of the distribution of the variance and the variance. The subjective Bayesian and the normal model with unknown mean and variance. Let's talk about now the subjective Bayesian and the normal model with unknown mean and variance. The subjective Bayesian framework provides little guidance about what prior distribution that one should choose. In a sense, that is the point of the subjective approach. It is simply subjective. You are free to pick whatever prior distribution you want, multimodal, uniform, high or low variance, skewed, constrained to lie between a certain set of values, etc. Why? Because this is a subjective notion. One of the key difficulties is that the prior distribution probably are not independent. That is, probability density of theta 1, theta 2, the joint density, need not be equal to the product of the marginal densities p theta 1 times p theta 2. For example, regression coefficients are generally not independent, even if that isn't transparent in some of the computer output like stata. If you want to incorporate subjective beliefs, the non-independence should be taken into account. Some general guidelines. we recommend the following general guidelines. Number one, if possible, use standard distribution, that is conjugate or semi-conjugate, and choose parameters that fix the mean, variance, kurtosis, etc. to be some desirable level. Number two, sample from the prior predictive distribution and check to see if your results make sense. Mechanically perform the following steps. 1. Take a random draw theta prime from the joint prior distribution of theta prime. Take a random draw y from the PDF y given theta with theta equal to theta prime. Repeat steps 1 and 2 several thousand times to provide a sample that you can use to summarize the prior predictive distribution. 4. Generate various summaries of the prior predictive distribution and check to see if the model's predictions are consistent with your beliefs about the data generating process. Okay, let us now talk about estimation of the lazy parametric Bayesian's approach to the normal model. Suppose yi is normal with mean mu and standard deviation tau for I from 1 to n. N is the sample size, where mu is normal 0t and tau is gamma ab. Actually, tau is here the variance parameter. By Bayes' rule, the posterior is proportional to the prior times the likelihood function. That is, probability of distribution of mu and tau given the data y is proportional to normal 0t times gamma distribution with parameters ab times normal mu and tau. The joint posterior distribution is really given as the product of those three. To estimate the marginal distribution from this model, it will be difficult analytically, but it's pretty easy to implement using the Gibbs sampler. Why? Because analytical expressions to integrate is not possible, so we have to go through a numerical approach, and the Gibbs sampler is that approach which will rescue us. So what do we need to know to implement the Gibbs sampler? In order to use the Gibbs sampler, we must identify the conditional distribution of the posterior, which is P of mu tau given y proportional to normal 0t times gamma ab times normal mu tau. In other words, we need to identify P of mu given y tau and P of tau given y mu. In this case, the conditional distributions are easy to find. So by definition, probability distribution of mu given tau y is equal to P of mu tau given y divided by P of tau given y, which will be proportional to P mu tau y. The proportionality follows because P of tau given y does not depend on mu. Therefore, to find the conditional mu for mu, we only need to pick out the terms from conditional distribution of P mu tau y that involve mu. We follow an analogous process for P tau given mu y. And there are long expressions given here, but you can see that essentially we can simplify, and if we assume that mu sub 0 is 0 and t equal to 1, then the joint densities or conditional densities will all simplify. So you will get the conditional distribution of mu given tau y is normal, and conditional distribution of tau given mu and y is the gamma distribution. So once we identify the conditional posterior distributions, we simply take random draws using the Gibbs sampling approach introduced before. So in this presentation, what you have seen is how to find the posterior distribution of mu sigma square jointly, and then conditionally the distribution of mu given the rest, given the data, and sigma square given the data. And you will already observe that we introduced a sampling based approach called Gibbs sampling, which is a special case of a Markov chain Monte Carlo method. And this Markov chain Monte Carlo method is a very powerful method. It's a computational based technique to avoid the analytical integration. And we demonstrated how to sample from each of the parameter from its complete conditional distribution, each of the posterior obtained, and therefore we can find out the posterior mean of each quantity of interest, that is mu and sigma square, and we can also find the credible interval or a confidence interval from a Bayesian point of view, how to find mu and sigma square, its interval estimate. And in next presentation we'll lay out the details of Markov chain Monte Carlo method.